Welcome to part 2 of week 6, in which we are going to discuss the analysis of Markov models. The analysis. And there are two ways of analyzing Markov models. One is called cohort simulation. Cohort simulation. And the second one is called individual or Monte Carlo simulation. And we're going to look in detail how these two types of analysis for Markov models work. So in cohort simulation, you usually model a hypothetical cohort of individuals with the disease of interest. Maybe you have 1,000 patients with nodding disease, and you model this hypothetical cohort to illustrate the experience of these patients as they go through cycles of the model. And you assume an initial distribution of patients amongst health states, and most modelers usually start with everyone in the well state. So if we had our 3-state Markov model and we had well, nodding disease, and dead, we would say maybe 100% of patients start here. Say everyone starts in the well state, and there's no one who's sick and no one who's dead. But sometimes you have diseases where you want to start the model with a proportion of patients who are sick. So maybe you have 80% here, 20% here, and 0% here. So you can distribute the cohort depending on the disease that you have. And when you run the model for many cycles, it builds a profile of patient distribution in the states over time, and we'll see how to do this. And the advantage of cohort simulation compared to individual simulation, what we call Monte Carlo simulation, is that it gives an exact solution for the chosen cycle time. If you repeat it many times, it will give you the same solution multiple times. The second way to analyze Markov models is individual simulation, and also called Monte Carlo simulation. And individuals go through the model on a one-by-one basis. So if you have our example, you have a patient who is well, or an individual who is well, and you have nodding disease, and you have dead here. So an individual might stay in well for 10 cycles and then move to nodding disease, and stay in 2 cycles, then die. Now another individual might move immediately to nodding disease. Or even more interesting one, an individual might get hit by a bus and go from well to dead in the first cycle, and that's the end of their experience. This is different from Monte Carlo, cohort simulation, in which you move proportions of people and distribute them between the states. And essentially, an individual can only be in a single state at a time. And the costs and outcomes are generated according to the path taken by a given individual and then averaged over maybe 1,000 individuals. And no run of the model can give you the same results. It always gives different results, and this is due to the random nature of the simulation. And this kind of analysis also gives an estimate of the likely variance associated with the model. And you can essentially estimate standard deviations. Now, the uncertainty in the estimated costs and effects relates to just the inherent probabilistic structure of the model, and this is called first-order simulation or first-order Monte Carlo simulation. Now, although it's beyond the scope of this class, there is what we call second-order simulations, which allow parameters to vary over a given range based on a distribution. So for every parameter, you have a distribution. Maybe it's a cost, and it's normally distributed, and for every run of the model, it goes and picks up a cost which might be maybe down here in the distribution or maybe up here. So it goes picking different estimates from the distribution. So that's a bit of an introduction to the difference between first order simulation and second order simulation. So let's give an example of cohort simulation, which is the first method and more common method of analyzing Markov models. And we have a Markov model for nodding disease, and the aim is to assess the cost effectiveness of a new drug for nodding disease. And this drug reduces nodding disease mortality. We also have a transition matrix, and we already talked about this matrix, so no need to go back there. So given the transition matrix that we have on the previous slide, you can assume this data, that the probability of going from well to nodding disease, so the incidence of nodding disease or the probability of getting nodding disease is 20% in a given year for this population. And then you have estimates of background mortality, and for 5 to 10 years it's maybe 0.1, and remember these are completely arbitrary, and then from 10 to 15 years it's 0.05 and so on. So you have the different background mortalities. Now these are very high mortalities actually, but we're using this for an example. And then for every cycle, 40% of people with nodding disease recover. And then the nodding disease mortality without treatment is 20%. And the nodding disease mortality with a new drug reduces to just 10%. So these are the data that we are given for this particular example. Let's discuss the assumptions for this particular model. We're going to assume that the starting age is 5 years and that mortality occurs in these 5-year increments. So the mortality rate used for the 5 to 10 age group, the mortality rate given for the 5 to 10 age group happens up to 10 years and then so on. And the other assumption that we can add to this slide is that the cycle time is equal to 1 year. So let this be our assumptions. Now it's important in modeling studies to set out your assumptions clearly so that your readers or your consumers can understand exactly how you came up with your results. We are going to do a hypothetical cohort analysis of the nodding disease problem, and we are going to do it for the no treatment side of the equation. Remember that we have the two comparators are no treatment and the new drug. And when you do Markov models, you run what we call the Markov trace for the no treatment and the new drug separately. And the difference between these from the last slide was that the mortality for nodding disease is 0.2 with no treatment, and it's 0.1 for the new drug. So let's run the no treatment Markov cohort as a demonstration of how the Markov trace works, how the Markov modeling works for a hypothetical cohort. So we have 1,000 patients starting off in the well state, and no patients starting off in the nodding disease state, and no one dead. And you have to keep track of the cohort. This is called the sum check. It's called the sum check, this column. So that's at cycle 0. At cycle 1, we know that the probability of nodding disease every cycle is 20%. So we have 200 patients coming down here. And we know that the background mortality is 10%. So we have 100 patients coming down here. And at the end of cycle number 1, we have 700, 200, and 100. And this gives 1,000. So our sum check is correct. Now, for cycle 2, it becomes interesting. Let's build up cycle 2, starting with those who are dead. So dead is the absorbing state. 100 all come down to this dead state. So you start out with 100 here. Now we know that the mortality from nodding disease is 20%. So 20% of 200 is 40. So we have 40 patients coming in here, and we have 40 here. So 40 plus 100 is 140. But we also know that there is a background mortality. So we have 10% of the 700 here coming down here. So we have 70. So 70 plus 40 plus 100 is 210. So we have our dead patients here. Now, these 200 who started out with nodding disease, 40 of them died. So those ones entered the dead state. But a proportion recovered, and the proportion who recover is 40%. So 40% of 200 is 80. So you lose another 80 here. So 80 go back to the well state. 80. So if those 80 go back to the well state and you lost 40 to the dead state here, that means that you have a balance. You have a balance of 80 patients. And these 80 patients come down to this state. So you have 80 patients. But the 80, you need to add those 80 to the patients who enter the nodding disease state from well. So we know that of the 700, a proportion of 20%, a probability of 20% of getting nodding disease will mean that 20% of 700 will come down here, 140. And if you add 140 to 80, you get 220 who remain in this state of nodding disease. So we have accounted for the nodding disease. Now let's account for the well state. It started out with 700 people in the well state, and we lost 70 to background mortality. We remained with 630. And then, in addition to that, we lost another 140 because they got disease. So 140 plus 70 is 210. So the balance would be 490. But we have to account for the 80 who came from the nodding disease state and got better. So 490 plus 80 equals 570, and we have accounted for that state as well. And if you keep doing the math, you can build up the different states, and at the end of 5 cycles, you see that nearly half of the patients are dead, and only 366 of the patients remain in the well state. And if you do this for enough cycles, everyone will end up, all 1,000 patients will end up in this state. Now, as you can see, what I've just gone through for a single cycle, if you have more states and you have more probabilities to deal with, it can be computationally difficult, and that's why we use Excel or other software like TreeEdge to do Markov models. And we're going for Monte Carlo simulation. We won't go through an elaborate example, but each individual is run through the model one by one. So if you have a cohort model, a Markov model, sorry, and you have well, and you have nodding disease, and you have the dead state, an individual in one cycle might go from well to dead. Maybe they are hit by a bus. But others might also do movements in which they go through nodding disease. So it depends on the individual's life story. And another individual might stay in the nodding disease state for multiple cycles. So keep staying in that state for multiple cycles. So every time you run an individual, they have their own course through the modeling framework, and that's called Monte Carlo simulation, and it's the second way of analyzing Markov models. So that's the end of part 2 of week 6, and in part 3 we are going to look at some examples from the literature of Markov models to see how a paper would look like and how individuals have applied these methods. Thank you very much. See you in part 3 of week 6.